Hi, this is Liang Qi. I'm an associate professor in Department of Material Science and Engineering at University of Michigan. My research is to apply theoretical and computational tools to understand the mechanical and chemical property of materials at atomic scale and nanoscales. Those kind of properties, in general, are not only determined by their crystal structure, but also by their defects, like vacancies, dislocation, and grain boundaries. There is a famous quote said that crystals are like people. It is those defects make them interesting. That's why a large part of my research is focused on applying computer simulation to study this complex material structure that contain many number and type of such defect. There is a famous paper by Nobel laureate Philip Anderson called "More is Different." This concept strongly influenced the philosophy and direction of my research.
So right now I'm studying grain boundaries in magnesium alloys. So I use methods like molecular dynamics in conjunction with machine learning stuff to look at how solute elements segregate at grain boundaries and how they affect the mechanical properties.
First, I would like to understand how multiple types of chemical elements affect these defect properties. For example, there's a new type of materials called high entropy alloy, which can contain 4, 5, or even more type of principal chemical elements. This high entropy alloy can be applied to construct more fuel-efficient airplanes or more safe nuclear power plants. But the problem is that we don't have too much understanding how this complex chemical element affect their defect properties, like dislocation or crack tip. That's why we are limited by their low room temperature ductility and formabilities. Right now, my research group is trying to build computational tools based on quantum mechanics calculation and machine learning to quickly predict how this complex chemistry affects its defect properties, so that we're quickly screening the alloy candidate for our experimental collaborator to do further verifications.
My PhD thesis would be about the aluminum alloy from first principle calculations to kinetic Monte Carlo simulations, and maybe to more applications such as the phase field simulations from small to the larger scale.
We also want to understand how, if you put many defects together, what's their properties. So even though we know many things about one individual defect, like one vacancy and one dislocation, but the collective behavior of many such defects together is still a big mystery. For example, right now people try to apply high-strength aluminum alloy or magnesium alloy in fuel-efficient cars or electric cars. But their limitation is that they have low formability and ductility, largely because we don't understand too much about the collective behavior of those defects, like vacancy added diffusion for precipitation or dislocation grain boundary interaction for their plastic formations. So my group is applying kinetic Monte Carlo simulation, atomistic simulation, and machine learning to study those defects from individual defects at atomic scale and their collective behavior at meso scales. The ultimate goal of my research career is to try to build a unified theory and models for those kind of defects. You may know all kinds of defects from your undergraduate course, like vacancy, dislocation, or grain boundaries. So there are already well-established theory for each type of defect. But still, there is a lack of a universal model or theory to predict their behavior together.
Right now I'm about to submit a manuscript, and I'm pretty proud and happy about it because it involves a lot of new methods that I learned over the past year, a lot of machine learning stuff, so I'm very proud of that.
So here I would emphasize this kind of defect study are not only important for structural alloys, but also important for many other applications like semiconductor, battery materials, and catalyst. My group will always welcome undergrad students and graduate students who have passion to understand the complex phenomenon in materials. So the materials, just like our real life, they are always not perfect. If you want to understand their imperfection, with quantum mechanical accuracy, please just contact me and let's have a chat.